So now we're gonna move on to week 6, week 7. So why we are still in the regression estimation? Well, because it's very important, right? So, so last week, week 6, we investigate the properties of regression estimator using 2 different approaches. So design-based approach, right? The Winston Lin, or I think Lin, right? 2013. So I mean, some design-based approach, and then model-based approach was so this is week 6 part 1. This is what week 6 part 2, right? And we discussed optimality, right? If you have a model, then regression estimator is derived, right? So basically the calibration, so mean part, error part. So mean part is control, can be made 0 by calibration. Calibration. So like this, right? Something like that. So this calibration imposed to control the mean part. Error part. So we covered something like this, right? I mean, minimize this. We want to minimize this, right? So that is basically came from the linear model, right? So we use this. If we use linear model, and EI is 0 and sigma square, then this is reasonable criteria because we assume equal variance. But if you know that the variance is unequal, for example, so if you know this is actually xi, for example, xi square, sigma is square, right? Suppose I know variance is xi square, sigma is square, xi square. Then I should, this is not good criteria, right? It makes sense to use xi square here to control the variance. So the whole idea is to minimize the mean square error. So that is the basically the reason. Okay. But that's not the end of the story. There are so many other things. And another thing we can consider to study this in today's class is to develop some kind of optimal estimation on the design-based approach. Design-based approach, we want to do optimal estimation. So, but we may want to consider a different class. So, so class here, the class is class is this one, right? In the model-based, the class is linear in Y. That is the class. But in the design-based, okay. So in the design-based, if you consider this class, then there's no hope. Because in the design-based, we know that this, suppose in the design-based, this is unbiased, design unbiased, then means Wi has to be 1 over pi I, right? No hope. If you use this class, we only have a single solution, a single element in the set. So the optimality does not make sense, right? How can we consider optimality when you have only one element? No. So we are not going to consider this class. So this is not our class in the design-based approach because that's not interesting, right? Okay. So now how we, the whole idea is we want to combine information essentially. So So then, natural question is where the additional information comes from, right? So where we can borrow information. So now we can see that so let's consider in the context of a CRE, although the same thing can be applied to survey sampling, but I will just explain everything in the context of experiment. CRE. So then t equal 1, we observe, okay, right? T equal 1, we observe xi and yi 1. T equals 0, we observe xi and yi 0, right? So that is our observation. And parameter of interest is mu1 and minus mu0, which is causal parameter in terms of the potential outcome. And then difference in means estimator. So direct estimator of the tau is just this one, right? So this is design unbiased. Okay. But you can see that you just use the sample only, right? This one uses sample, t equal 1 sample. This one uses t equals 0 sample, right? So it doesn't really use the additional. So maybe there's some room for improvement. So idea is, so how to utilize the observable information? Well, let's introduce another parameter, mu x, which is the population mean of x, and compute an estimator of mu x from each sample. So that means, so previously here is this is more like individual level, right? The information in the unit level, but here the information in the set level, sample level. Okay, so in the sample, right, t equal 1 sample, which is the treatment group, I can compute two estimators. One is the estimator for x, and the other one is the estimator for mu1. Okay, so this is also design unbiased. Control group, we can also construct two estimators, which is a design unbiased for mu x and mu1, mu0. Okay. So I have four estimators, 1, 2, 3, 4. I have a four estimator, and how many parameters? 3 parameters, right? Because mu1, mu0, mu-x. So 3 parameter with a 4 estimator. So I have additional, information, right? If I have a 3 parameter for 3 estimator, there's nothing we can do, right? There is the information is fully, just identified, so we cannot really borrow any information. But here we have additional information, right? 4 estimators, 3 parameters. So we can do combined information. So usually the usual technique is to use some kind of a linear model, right? Construct a linear model. So you can construct a linear model. So you have a basically 4 observation. You can treat it as a 4 observation. So you have a 4 random variable, right? 1, 2, 3, 4, and 3 parameter. 1, 2, 3. Okay. So then how we can connect, right? We know that this is, at least we know the expectation easily, right? Okay, so this is expectation. So I want to write this expectation as a linear function of the original parameter, right? So that is this one. So this one is this guy, right? And this guy. So basically, see, let's check. So if I multiply mu x, mu one, mu zero, right? So then this is a p dimensional vector. This is a scalar. This is a scalar. So that means I can so this is the column. We have a p plus 2 column. Here p plus 2 row. So it matches, right? And then this guy times this guy is mu x. Second row, this guy times this 0, mu 1, 0, right? So that basically so this is okay. Well, now our goal is to combine this information, right? Combine this information. So as a linear way, I can consider linear weight. So weighted sum of this original estimator and combine in an optimal way. So that basically means I can use some kind of a GLS method, right? Generalized least square method. So I can this is my initial, right? So this is the initial estimator. Let's call this initial estimator. Or direct, right? Or direct and unbiased estimator. And then I need to identify the mean structure, right? So the mean structure is this one. So this is actually nothing but expectation of design expectation of theta hat. And right, and that turns out to be a linear function of the parameter of interest. And then this is V is the variance covariance matrix of the theta hat. That way it gives the optimal, right? Minimize the two. We want to find the estimator that minimize the variance among the class. Okay. So this is 10 problem, right? And we know the solution already. I assume that you know the solution. So I'm not going to prove it again. But the idea is basically the GLS estimator is X. Oh, no, here is G times theta hat GLS. Oh, oops, sorry. So no, okay, not this way. So so theta hat GLS is more like I think notation is not really it's a little bit confusing, but let's use beta. Then you can you can view it as a not okay, not this one. Okay, so here's my best estimator of the theta. Well, okay. I think I actually get myself confused. So this is actually what what is the solution to this? If I write it better, then the minimizer is C prime V inverse C inverse C prime V inverse Y. I mean, if it is, so if I write it as a Y minus C beta prime V inverse Y minus C beta, right? So if I write it this way, Q beta, and then the minimizer is GLS estimator is C prime V inverse C inverse C prime V inverse Y, right? So that is should be 5 10 result. So that's exactly this one, right? That's exactly this one. So we just call it so you can call it Y or you can call it zeta hat. So we use this one. Okay. So now, so I think in the conceptual level, right? In the high level, that's it, right? This is all we want to know. But when it comes to actual computation, right? When it comes to actual computation, the computation for our specific case, for our specific example, we need to solve this, right? We need to solve this, but which requires some computation, I mean, skills. So here's some tip. So I have a, I try to deliver as many tips in my class as possible. Some of the tips are really not really in the textbook. So hopefully you can. That's the benefit of taking a class, right? From me rather than studying by yourself, right? If you study all your by yourself, then it's hard to learn the tips, right? I mean, so here's a tip, basically. Okay, so let's simplify the problem and suppose this is our problem. So this is more like general setup. Okay, so idea is, okay, I have two estimators of, so this is my, I have two parameter. I have two parameter and three estimator. Okay, so something like this. So when you're asked to solve this question, so when you're asked to show this, okay, so suppose you're asked to show this result. So this is the first result is that the optimal estimator of mu can be a weighted average of the x1 hat, x2 hat with this particular weight. Okay, that's the first result. And second result is that your optimal estimator of the mean of y is take some kind of regression form, regression prediction form. So that may make sense, but it's not really probably not really obvious. You cannot really solve it from your head directly without working out the details. But let me give you some very interesting tip. So idea is, so how can we basically, how can we solve this, right? How can we solve this in practice? Suppose this is your PhD thesis. So when you solve, when you write a paper, PhD, write your thesis, you encounter suppose you encounter this problem, right? Then you need to prove it. And then how to prove it? Well, here's a tip. So this guy, which is this guy, okay, mu x, mu y, can be factorized. Okay, this quadratic term can be factorized into two parts. Okay. And with this. So I will prove it soon. So for now, let's believe it. Okay. Let's just assume that this is true. So let's just accept this one. Then why this is convenient? Okay. So why this is convenient? So why finding the minimum of the right side is easier than finding the minimum of the left side? That's my question. Okay. Why? Because if you can find the mu star minimizer, so basically my point is that minimum over mu1 and mu2, mu x and mu I, right? So this is joint minimum, but you can actually see. So what is the point of considering mu I for this guy when it is only a function of mu x? Not necessary, right? You don't have to worry about. So the problem, so bivariate optimization problem becomes a univariate optimization problem. This is supposed to be easier, right? So then basically once so idea is you can do it step by step. So you can make this one, find the optimizer, and then find the optimizer for the second one. So that's basically the idea. So now, okay. So that kind of, so now you understand why I try to do it, right? And the next question is, why this happen? So how can we show this? Where this equality comes from? Here's actually I covered this in my 523 class. So so actually this is a part same. Actually, I use the same. Yeah. So if you took my class 523 class already and still remember, you have to remember it too, right? So still remember, then this part may be bored, but otherwise you can find it interesting. So my point is that, well, what is the Q, by the way? This Q is a core part of the joint normal distribution. So joint density, think about that, joint density of under normality. If you think about that. So what is the density function? What is the density function of the joint normal distribution? You have something, right? You have something, but end of the day, you will have a Q. Okay. Right? End of the day, you will have Q. Minus half, exponential of minus half, and Q. Okay. Then, what is the nice thing about joint density is that marginal and conditional are also normal, right? So this guy is nothing but, so this is a joint density. So whole part of the joint density, this is a marginal density. This is a conditional density. So actually, when we derive the marginal density of the Gaussian distribution, we use the formula for the partitioned matrix, inverse of partitioned matrix, when we derive that. But now that we know, right, as a statistician, as a statistic major, we know the formula, right? The density of the Gaussian distribution formula already. So we can just use it. And so the basically this is you can see that this is the Q1 is nothing but the marginal density, and Q2 is nothing but the core of the joint density. I mean conditional density. That's it, right? Okay. Now, what is the minimizer of Q1? So minimizer of Q1, this is maybe a doable, right? You have a 2x2 matrix inverse, so that's probably not really difficult. So that gives this solution, and then mu2, so mu(y). So second one, the minimizer of the this guy actually has this. So idea is you first plug in, right, mu x star, plug in, because the minimizer, so because we want to minimize. So that means you need to first obtain the minimizer of Q1 and then plug into here. And then solve only for mu(y), okay? And that will give you your answer. So that gives us this form. Okay. Yeah, so that is the basically. And now that is for general case, but we want to apply to our problem, right? We want to apply to our problem. And in our problem, we can decompose mu x mu(y). So let's go back to our problem. What was our problem? Our problem was this. Okay. So this guy has to do with x, right? This guy has to do with y. So you can call it mu(y). Okay. You can call this mu(y) and factorize. And then apply. So then this is Q1 and Q2, same thing. So Q1 is this guy. Q2 is this guy. The form of VEE is not really important in our problem because we want to make it to be zero. That means we want to make this guy to be zero. Anyway. So yeah. So here's actually let me explain further. So here the minimizer is not equal to zero. Because why? Because you never make this one exactly equal to zero, right? Because you have two information, two estimator with one parameter, right? So you cannot really make this one zero. But here you have a one parameter and one estimator. So you can always make it zero. You know my point? So this is, see, this one has two estimators, right? You have two estimators for one parameter. So you never really there's no way you can make your estimator, right? Optimal estimator can make this one Q1 exactly equal to zero. That's impossible. However, this one Q2, you can make it exactly equal to zero because you have a one unknown and one information. Okay. So okay, so in our problem, so key part is, so what is this one, by the way? What is B1? This guy is 1 over N1, I equal to 1 to N, Ti Xi, right? This guy is 1 over N0, I equal to 1 to n, 1 minus ti xi. Okay, so we need to compute the variance covariance matrix. So let's check where did we get this. So variance, what is the variance of mu hat 1? So variance, this guy is 1 over, let me write it again. Right? So that is a variance of expectation plus expectation of variance. Sorry, let me write next page. I think this is probably, so variance over x mu hat x1, so is variance of expectation over mu hat x1 given we are talking about design base, but the parameter is actually superpopulation parameter, right? Mu x is a superpopulation parameter. So this guy is 1 over n, I equal to 1 to n plus 1 over n1 minus 1 over n something like that. So this, so basically where p, so point is here the randomness is with respect to t, right? Conditional on f. The only thing random is treatment assignment. So sampling. Okay. Here, the randomness is about the superpopulation. So this guy is 1 over n sigma xx plus 1 minus n minus 1 sigma xx. So that is 1 over n1 So by the way, sigma xx is where expectation over x minus mu x population, superpopulation, so variance of x in the superpopulation model, right? Variance covariance matrix. Superpopulation. Okay. So if you do this way, let me you can do the same thing, right? So then this way is a expectation of the you had x1 0 plus covariance, expectation of covariance right? So this guy is actually, this is x bar n. This guy is also x bar n, right? So this one has to be 1/n sigma xx. And second term, oop, I think I can, right? Okay. So is minus, remember something like that, right? Xx squared. The covariance. One is a sampled part and the other is the non-sampled part. And the covariance between can check. So this guy, expectation of this guy is equal to this guy. So they will cancel. That's why you get a 0 here. So then the inverse, right? V inverse. So the weight actually 1/n1 is actually inverse. So you get your final estimator of a mean of x is indeed a population mean of x, which makes sense, right? You end of the day, your best estimator for the mean of x combined everything should be the population mean of x, right? Makes sense. Should make sense. Okay. Mean of y. So we wanna compute this one. So this one involves some matrix. So this guy, right? So this is what you want to compute. And then same way, you can obtain something like this. So basically you have there's a correlation, covariance, right? So in the same sample, in the one, you have a covariance and the sample size is n1. 1 and 0, end of the day it cancels. So you have 0. And then you have this one. I already explained this, right? So combined, you get something like this. So then we can actually apply the formula here, right? This is our formula. Formula is what? Formula is mu y star hat star is an initial estimator minus b mu hat x minus mu x hat star, right? So this is our formula. And then we here, this is a two-dimensional vector, right? 1 and 0. So that is this one. So basically mu hat star y is a mu hat y initial estimator minus p, and then mu hat x minus mu hat x star. So this guy is this guy. This guy is this guy. And this guy comes from here. And this guy is This guy. So that basically gives our final estimator, GLS estimator of this of the tau, which and now we know that this is actually y by x by n, right? So we after some algebra you can actually obtain. By the way, this one is not really estimator because B1 and B0 are superpopulation quantity. So they are unknown parameters. So this is not really estimator, but you can estimate it from the sample, then you can construct the regression estimator. So this even end of the day, it actually justifies regression estimator. So we end up getting the same estimator, but the motivation is different. Now it has an interpretation of the combining best combined, right? Best GLS estimator, right? GLS estimator of the design combined estimators. Okay. So that is this. So this involves a lot of algebra, right? You have to compute all the variance covariance metrics and but you end up getting the same result. Here's another way. This is really, really interesting. I discovered this recently, so you should feel lucky because if you took the class last year, then I realized this technique last week, something like that. But anyway, okay. The idea is, so remember, how did we compute this, right? How did we compute all this? We used the GLS formula. We used the GLS formula, right? But where the GLS, here's another interpretation of GLS formula, basically. So another interpretation of GLS formula is that you can, okay, so this is parameter of interest. This is the initial estimator. And we know the mean structure, right? We know the variance covariance matrix. And then our ultimate goal is to find the optimal omega hat that combines our initial estimator. End of the day, right? This is what we want. So how we compute it? Where previously we used basically use the GLS, right? GLS formula G prime V inverse G inverse G prime V inverse, right? Set ahead. But if you use this formula, then it involves a lot of matrix algebra. Okay, but here's a different way. Different way is that you can actually formulate it as a constraint optimization problem. And the constraint is this. Okay. Let me ask you a question. Where this constraint comes from? Yeah, so you mean the mean structure, right? Yeah, that's very good, right? So actually, this is another way of writing the GLS, essentially. Why? Because we know. 。 right? We know that. But our parameter of interest is so C theta, right? So parameter, okay, no expectation actually. So if you write it, right? But this is our parameter is actually this one. So we should omega prime C okay. We want this to be equal to C prime theta. Okay, right. So whatever omega, right? Whatever omega, if this omega is a best estimator for tau, is a best estimator for tau, it should satisfy the expectation should satisfy equal to tau. Right? So we want this guy to be equal to tau, right? But what is tau? Tau is this one. Okay. And then theta is unknown parameter. So you can actually, this one should hold for all theta. So that means you can actually cancel. So that means omega prime z equal to c prime, which is this. So this is just another way of writing the GLS, right? But you write it in a way that easy to explain, easy to understand, explain in terms of the weight. So in the language of weight. So the optimization was written in the language of weight. I will explain the prove it later. But why this is interesting? Because so then if I write it as a so okay. What I care is about estimation of tau, right? So and I know that my estimator should be a linear function of the available estimators. So this is my available estimator, right? This is my available estimator. I want to construct a linear combination of the available estimators. And I want to impose unbiased condition to reduce the number of unknown parameters, right? Reduce the number of weight. So actually this is my constraint. So my constraint simplifies the weight so that end of the day, I get this. Okay. So that means originally this was looks very complicated, right? But using this one, I can simplify. So I can simplify end of the day something like this. I have only to find the omega 1, optimize with just omega 1. That's my solution. And then this guy, so I can solve this optimization problem. And this one is this one. And then we can check that two estimators are same. So which one is easier, right? I mean, here I only use the 2-page, but here we used a lot of algebra, right? So I thought the second approach is easier to derive and in practice, but you can. So I will cover this a little bit further this Thursday, and then move on to the part 2. Okay.